Next, we get into details of instruction format. By this information, we know what is the largest number that can be stored in each part of instruction, and that tells us the range of possible address the instruction can reach. Right? Don't have to worry about the name of the format, but for all those instructions that we show you previously, all of them have 5 operation code, 5 bit. 5 bit means 32 different operation code. Okay, and for the last type, of course, 32 kind of instruction is not enough, right? Modern CPU have say 200 something. So to extend that, we have this kind of trick. We specify some code that we can have another 12 bit to extend to different kind of operation code. Okay. Let's start with the first one. If this is the large format, we use 22 bits to specify the address. Therefore, we can directly, right, access anywhere in the RAM in our main memory at a 22 bit or just 4 million. Okay, because our CPU is on the 32 bit boundary, is not, it has no byte address. It's not like the Intel CPU. Okay. The next format is probably the most popular one. If you remember tree address, we have this format to specify all the operation in tree address. Okay, this one with the immediate value of 17 bits, and this one is specify all the tree register. And if you notice, we have 32 registers, so we need a 5 bit to specify it. You don't have to worry about these details because when we program, we write it in assembly language. We are not going to worry about how big this number. But if you know about this, then you know what is the largest number you can use in that kind of instruction. Okay, let's start off using this instruction to compose a few programs. Okay, this is, well, just a few more slides, so don't worry, just bear with us. Maybe less than 10 minutes. Okay, so the first example will be simple statement A equal B plus C. In this first example, we assume that A, B, C are local variable. So we keep all of them in register. Okay. To specify, to program assembly language, you need to specify the register. So in our instruction, we have only register, right? So we need to know what register associate with what variable. Okay. So this line is important, otherwise you cannot read the instruction. So let's say we use R1 to keep A, R2 to keep B, R3 to keep C. So these statements become just one instruction. Okay, add R1, R2, R3. Next will be next example will be a bit more complicated, right? The same statement, but A, B, C now become global variable. We store
พูดปิดเสียงไมค์กูยังไงวะ
ABC as global variable mean they are stored in the main memory. So in this example, we assume they are at location 100, 101, and 102. We use R1, R2, R3 to store those values temporarily, okay? Because when we want to operate them, in the example, we want to add them, we can add only the value in register. So the first thing we do is to get the value from memory into register. So we get the value from location 101, which is variable B, and next is location 102, and then add it together. Keep it in R1. Then we can store the last thing we store R1 back to the memory at 100. Okay. You can see that the operation concern the memory require separate getting and setting the value. Okay. It is unavoidable. Not everything you keep in register. You have only 32 registers to use at any time. So you always have to move the value between main memory into the register. Next one concerns the control, right? So we illustrate using simple loop. Let's say we want to add number 1, 2, 3, 4, 5 to 10. Okay. How to write the sequence of machine code to do that? The easiest way is we are not going to use any branch instruction. Okay. Let's say we use R1 to be the sum. Right? We can just starting with the clearing or moving a 0 into R1 and then add 1 to it and then add 2 to it and add within 10 instructions. You are going to get the result in R1. This is the most straightforward and the fastest way to run this program. Right? There's some annoying factors such as this sequence will sum only 10 number. If you want 20 number, then you have to change the program. Okay. So let's using the repeating the instruction to shorten the program. We can write those kind of program as a pseudocode. We use a S to keep the result and use I to count the number of times that we repeat it. So we want to sum number 1 to number 10, then we repeat it 10 times. Okay, so we use a loop as if as long as I is less than or equal 10, then we keep adding I to the sum and then increment I by 1. Okay, this can be achieved by using this sequence of machine code. First of all, we have to assign the register. This is important. You should make yourself a habit of writing this out by hand. Okay. We use R1 as S, R2 as I index, and because there is a test of I less than or equal 10, we have to keep the result somewhere. So we use R3 to do that. First line, we set S equal 0. Second, set I equal 1, second line. And then this is a what called label. Label is just a kind of a signpost, so we know where we want to jump to. Okay, it will be handled by assembly. We call assembler, a program to convert this into machine code that can be executed. Okay, we will use that next week. And to perform the test, we use less than or equal between I and number 10, and the result, whether it's true or false, will be stored in R3. Oh, I make a mistake. this is jump 4, you have to specify R3 here, okay? I cannot really correct my PowerPoint right now, but this is, you need to specify a register, a value that you want to test here. So it's jump 4, R3, exit, all right? If it's not true, then the loop stops, so it jumps to the end of the program. Otherwise, it just sum I into S, and then increment the I, and then jump back to the beginning, okay? So it keep running for 10 times, then the program will finish. Last example, accessing array. This will show you how we use the getting the data from an array. Okay. So let's say we want to sum all the elements in the array of 10 numbers. Okay, and so we write in high-level language something like this: AX is the array, and that's, wow, we are running out of time again. But we will finish before that. Don't worry. Okay, so again we said we clear the sum starting the index. Now the index of this array start from 0 to 9, all right, as a normal for modern day programming. So we now check if the index is go to the end of the array, so it must be less than 10. Be careful, this is less than, not less than or equal, right? And then we access the array and then get its value and then sum it, and then increment the index. Next slide show you the assembly sequence. How we access the array xi. So let's assume that the array start at the location 1000. We can use this instruction load with the index addressing. So we use R4 as the location of the array and R2 as index, and then we write this way. So this will get the value of one element into register number 5. Okay, so let's explain the whole program in detail. First of all, we have to write this line. Okay, you write it for yourself to understand your program. We use R1 as sum, R2 as index, R3 as flag. And because we have to store the allocation of array, we use R4, okay? And then because we have to retrieve the value of the array, so we use R5 to store the value of the one element of this array. So let's begin. We clear the sum. We start the index at 0, and then we set the location of the array. And then the loop, we test if index is less than 10, and if not, when we jump to the exit, is again require jump 4 R3. I will correct it later on when the lecture finish. And then we get one element of the array and then add that to the sum, increment the index and jump the loop again. Okay. I think that's the end of this lecture. The most